Hello. This is my lab report for Lab 6, Magnetic Molasses, and my name is Krish Gandhi. So, to start off, the main introduction of this lab is we were trying to see and observe how magnet falls through a conductive aluminum foil tube and to simulate the magnetic magnet tube interaction using glow script and to compare the simulated results to our experimental data. Oops. And then our purpose and summary of the results. So the purpose of the lab is we're mainly looking at Faraday's law on an object. So Faraday's law in general relates time-varying magnetic field to a curly electric field whose path integral around a closed path is not zero, but it does provide an EMF to drive the current. The current consequently creates a magnetic field, which will put a force onto the source of the external magnetic field. In the lab, primarily though, we're looking at how the source of the external field is a falling bar magnet, and the induced current is driven in the tube of aluminum foil. The interaction between the magnet and the tube creates an interesting result, which we'll see later. The expected results can be seen with how the fall will be slowed briefly because of Faraday's law. So here's some fundamental models and principles of the lab. There's Faraday's law, which is seen with those equations right there. There's the change in magnetic flux, the position update formula, the magnetic field of a bar magnet, and the magnetic force on a wire loop. So those are the respective formulas alongside those. You can take a look at those. The system, there's bar magnet and aluminum foil tube surroundings for everything else. Procedure, initial conditions. We have the aluminum foil vertically and put the magnet above it. We recorded using a smartphone for the time. We looked at the video for the timings as well, and we calculated the time it took the magnet to travel, and then we repeated for 5 times, and we found the average. Here's an image of our experiment, and then our results for each trial, and our mean of 0.3165. Here's some of our code. It's a little bit hard to see, sorry, but yeah. This was the output of our code. It's a velocity time graph. It's just saying that like it starts at 0, exponentially decreases, kind of like in a reverse sinusoidal graph. Yeah, set with the average of 1.1. Okay, here's the similarities and differences between the models. So in the real life magnetic molasses experiment, the motion of a charged bead in a viscous medium is influenced by a bunch of imperfections that you can't see in the code. Experimentally, experiences like friction, there's tilts, misalignments, things like that will have an impact on the experiment itself that you can't really replicate through code. And the real bead also interacts with the actual magnetic field gradient, like physically, and that might cause like deviations from ideal behavior. The code, however, is perfectly controlled with the magnetic force and gravitational contributions without noise or hardware limitations. And the model treats the magnetic field as uniform when that may or may not be true, when there's like friction or turbulence involved. So the simulation is a lot cleaner than the theoretical predictions. Yeah, so the code is more theoretical. So here's some errors, could be misalignment in um, equipment, user error, measurement error, timing, things like that. So the first what if question is what if the resistivity of the conductor were reduced to 0 or close to 0? And if that happened, kind of like a superconducting material, the dynamics would change. Um, the induced currents would encounter like no resistance, allowing them to go without like much decay. And these currents would create strong opposing magnetic fields with Lenz's law. So it will create like a maximum magnetic braking. So what if the holes were cut into the tube? How would this affect the ring currents? So inducing these slots would disrupt the path of the ring currents, and since these currents rely on closed paths, the cuts would force the current to either stop or become less efficient for broken paths. So the magnetic field would weaken and decrease the opposing force on the falling magnet, which would cause the magnet to fall faster. Thank you. That's it.